Okay, this is going to be part 2 of the video on the root test for convergence. And if you haven't done it yet, I would definitely watch the first video because it runs through some fairly simple examples and shows you where the rule comes from. Now in this video, we'll take a look at a couple of other problems, a little bit trickier problems. And again, reminder before we get started, what the root test says is that if you have some series, if you can show that the limit of the nth root of that series is less than 1, actually the absolute value of it is less than 1, then you can show that the series converges. If the limit is greater than 1, it diverges, and if the limit is equal to 1, then the root test fails. So again, if you're not familiar with this, watch the first video just to get you started on this part, then come back to this video and we'll do a couple of extra problems. Okay, now the first problem looks like this, and actually we're going to work this 2 ways because I want to make a point here as we go through it. A little bit trickier than the ones we've done before, but it's the same problem here and here. Let's work it 2 different ways because there's a couple of approaches that you can do on it. So the idea is, given a problem like this, and I think I'll go over here to the side and put this in, what the root test is usually good for, we talked about this in the first video, if you have something, some sort of a series raised to the n power. If you've got something to the n power, then the root test is a great test to apply. But some students think that you have to get it in the form 1 something to the nth power before you can use the root test, and actually that's not true. So we'll work this 2 different ways. The first way, we'll actually manipulate it into this form where it's something to the nth power. The second video, second example here, we won't do that, and we'll work it without, first of all, changing into that form. But in both cases, we should get the same answer. So again, let's kind of run through our steps. Just like in the first video, the first thing I do is, since the original series could be have some negative terms, we'll take the absolute value of it to make sure that it's all positive. Now, if you're lucky, the original series will be positive, and that's what happens in this case. So in this case, n is always positive, so the way the series is set up, no matter what you use, it's always going to be positive. So on this one, you'll know this. You will know that the absolute value of the original series is the same thing as the original series, so nothing changes there. So first of all, I'm going to manipulate things just a little bit. So starting with this one, I think I'll do this. I'll make this be equal to the summation, and I'm going to change things around. I'll make it be, I'll think of this as being, now think of 3 to the 2n, and what I'm trying to do is to get it in this form with an n out here all by itself. So I'm going to rewrite this as 3 squared raised to the n power divided by n to the n power. Because remember, if you multiply them, a power raised to a power is like multiplication. So that turns into that. This goes from 1 to infinity. Now what that's going to give me would be this. So summation from n equals 1 to infinity. Now 3 squared is 9, so I'd wind up with 9 to the n divided by n to the n. And I can write that as the summation. Now again, since they're both to the n power, I can write this as n equals 1 to infinity of, and I'll make it be 9 over n raised to the n. So all I did there is, here was the original series, and I just manipulated the series until it turns into this form. And if you want to do that, that's not a problem at all. You can do it. Once you've got it in this form, it just shows that it's a great candidate for the root test. So now let's apply the root test. So what this is going to be, it would be the limit as n approaches infinity of the nth root of this right here. So I'd have 9 over n raised to the nth power. Now again, by manipulating it into this form, it's particularly easy because if you do that, the nth root and the n always cancel out, and that just gives you the limit as n approaches infinity of 9 over n. Now, if you take that limit as n goes to infinity, the denominator is going to get larger. This entire thing is going to go to 0, which says that this is going to approach 0. Now, looking at your rule, you found the limit was 0. The rule says that if the limit is less than 1 and 0 is less than 1, then the original series converges absolutely. So since that is less than 1, you have showed that the original series, so the original series converges absolutely. So now what this was starting with this problem, and all of this part right in here was just manipulating it to get it from something that doesn't have an n on the outside to something that does have an n on the outside. So you changed it from this form into this form, and it wound up looking like this. And once you got it in that form, then you applied the rule, and everything worked out just fine. Now, the point I want to make on this is you don't have to go through all this steps if you don't want to. Just because it's not in the form of something to the nth power, you can still apply the root test to it. So let's just start with this and apply it. Now, in this case, again, same thing is, since it's all positive, the absolute value of a sub n is going to be the same thing as a sub n. So it just turns out, since the original series was positive, its absolute value is positive. But this time, let's work on the original problem without going through all that manipulation first. So this is going to go to infinity. I'm going to have the nth root of, now the original problem was 3 to the 2n divided by n to the n. But you haven't put it in this form up here. We haven't changed it into this form. So let's go ahead and see what that looks like. So we want to find the limit as n goes to infinity. Now I'm going to change this nth root into this thing to the 1 over n power. So this is like having 3 to the 2n divided by n to the n. The whole thing raised to the 1 over n power. That's what it means when you take the nth root. Now at this point, you can individually take both of these to the 1 over n power. So I'll make that be the limit as n goes to infinity. And it's going to be the numerator raised to the 1 over n power divided by the denominator raised to the 1 over n power. So what that's going to give you is going to be the limit as n approaches infinity. Now again, whenever you have a power raised to a power, let's just kind of go off the side and do that one. You multiply the exponents. So that's like having 2n times 1 over n. The n's will cancel out and leave you with 2. So in the numerator, this would be like having 3, and this exponent all combined together will turn into a 2. Now do the same thing down here. In the bottom, you've got n times 1 over n. The n's will cancel out and leave you with a 1. So when you multiply these together, the denominator turns into just n to the first power, or n. Now what that's going to be, we'll kind of bring it back down here, that would be the limit as n goes to infinity. And 3 squared is 9, so you'll wind up with 9 over n. Now you might do this. At this point, notice, here's the limit of 9 over n, and up here is the limit of 9 over n. So eventually you'll get to the same spot. So again, if you take this limit as n goes to infinity, then this term goes to 0, which again tells you the same thing. The limit's going to be 0. 0 is less than 1, and you can draw the same conclusion that you did up here. Since this is less than 1, that tells you that the original series, so the original series converges absolutely. So the original series converges absolutely. So again, you get the same answer on either one. So the point I want to make here is that don't feel that you need to take the original function and manipulate it into this form before you apply the root test. If you want to, just start with the original thing, and when you have the nth root, change it into 1 over n, and just use your exponent rules, and you'll still get the same thing. So anyway, there's the first example. It's almost like you can put a line right across here. And 2 separate problems, or same problem, solved 2 separate ways. Okay, let's take a look at the next example. And this one's going to be a little bit trickier still. Now we're going to do the same thing. This doesn't look like, again, we'll go look at that form. This does not look like something to the nth power. So at first it may not seem like a candidate for root test, but the fact that it's got something to the n power in here, and here's a power of n, even though it's combined with something else up here, pretty good hint that it still might work. Now again, first thing to do is check the absolute value. So what I want to know is, if I had the original series, if I changed them all to positive terms, what would it look like? Well again, on this one, no matter what, since n has always got to be greater than 0, no matter what you put in here, that's always going to be positive. So that tells you that the original series only contained positive terms, so the absolute value of the original series is the same thing as the original series. So that makes things just a little bit easier. So now we'll go ahead and apply the rule. So you want to find the limit as n approaches infinity, and what we're doing is just this step right here. You want the nth root of the absolute value. So this is going to be the nth root, and I'll make a kind of a big one here, of the original series. So this will be 4 to the 2 plus n divided by natural log of n raised to the nth. Again, the first thing I'll do is make this be the limit as n approaches infinity. And rather than the nth root, I'll rewrite it as that whole thing to the 1 over n. So just change it from an nth root to a 1 over n. Now inside here, it'll still be the original. So this will be 4 to the 2 plus n divided by natural log of n to the n. So it looks like that. Now again, what this is just each thing raised, the numerator raised to the 1 over n and the denominator raised to the 1 over n. So I'll make this be the limit as n approaches infinity of, now first of all, we'll take the numerator. So that would be 4 to the 2 plus n, this whole thing raised to the 1 over n power. Then in the denominator, do the same thing. So the denominator is the natural log of n. Originally it was this, and now we're going to raise that to the 1 over n power. So again, raise both the numerator and the denominator to the 1 over n power. And now it's just a matter of playing around with the exponents. So you've got the limit as n approaches infinity, and we'll write this like this. In the numerator, you would have 4. Now again, when you've got a power raised to a power, you multiply. So this is going to be 2 plus n times 1 over n divided by the natural log of n. Now on this one's actually a little bit easier. Well, we'll go ahead and write it down one more time the more I think about it. Originally it was the n power. Now again, it's going to be n times 1 over n. So again, a power raised to a power, change in multiplication. A power raised to a power, change in multiplication. So that becomes the limit as n approaches infinity of 4. And what you're going to do here is go ahead and distribute this 1 over n. So I'll have 1 over n and 1 over n. So what that's going to be would be 4, and this will turn out to be 2 over n. So 2 over n plus, now this will turn into a 1. So it's actually 4 raised to, and if you want to, you can put in parentheses, that power. Now, in the denominator, these n's cancel out and just leave you with this thing to the first power, which would be the natural log of n. So we can put parentheses around this entire thing. So now you're ready to take the limit of this thing. So what's this going to be like when you take the limit? So if you take the limit as n goes off to infinity, then just looking at this 2 over n here, you've got 2 divided by a number that's going off to infinity. This 2 over n will go to 0. So that's going to leave you with, in the numerator, you would have, since that went to 0, now all that's left is 4 raised to the first power. So that's going to be a 4. Then in the denominator, if you take the limit as n goes off to infinity, the natural, as n gets bigger and bigger, the natural log of this thing is going to get bigger and bigger. It's like having an incredibly large number or infinity. So 4 divided by a very large number, this whole thing is going to go off to 0. And then since 0 is less than 1, then by your test, you showed that you took the limit's less than 1, therefore the original series converges absolutely. So at this point, you can draw the conclusion that the original series converges absolutely. And again, the trick on this is change this nth root end to end of the 1/2, and really just it's all applying the exponent rules from there. Apply your exponent rules, take the limit, and you'll get an answer. And again, depending on if it's less than 1, it converges. Greater than 1, diverges. If it's equal to 1, then the test fails. And in the third video, we'll take a look at one more case with a special case of the root test in which it will fail, and there's a couple of other little things in there too. So one more video to go on the root test.